Okay, so we're talking about functions, which ones grow faster, slower, or the same rate as x approaches infinity. Okay. So basically, we're just going to compare the two functions. If the numerator over the denominator gives us infinity, then f grows faster than g. And we're talking about rates. So for example, take like something linear versus something exponential. Which one grows faster? The exponential. Okay. So those are the kinds of examples that we can look at. Or you can compare like an x squared, right? Compared to y equals 2 to the x. Right? Which one's going to, that's not supposed to go below, but you get the idea, right? Which one's going to grow faster, the exponential or the x squared?
The exponential.
The exponential, for sure. Okay, versus what if we put g of x on the top and f of x on the bottom, then we should get 0. So it doesn't really matter which one we put on the top or the bottom. It depends on what we end up with as our result. Okay, so if we put the bigger one on top, then we should get infinity. If we put the bigger one on the bottom, we should get 0. Here's an example, right? So there's not much work to show here. Okay, so that's the thing about this lesson. It's going to be comparing degrees, or possibly we might have to apply L'Hopital's rule. So here, what do we get? Infinity. Therefore, x squared plus 1, we say grows faster than 3x. That's all. Okay. And what if, when we compare the two, we get a limit that's not equal to 0? We say they grow at the same rate. Okay, so any real number, as long as it's not 0. So an example, 2x minus 5 over x plus 4 gives us 2. Therefore, 2x minus 5 and x plus 4 grow at the same rate. It's just end behavior.
Aren't you just saying which slope is bigger? What?
Okay, but the slope is changing. So the slope might be steeper at 5 for one function versus the other, but we're looking specifically as we approach infinity. So it's the end behavior of the graph. I mean, you're right. You're thinking about slope, but the slope can change depending on what the value is. So we just want to know what happens as x increases without bound. Okay. All right. Good? You get the idea? That's really all that it is. Okay, and then we'll kind of summarize which functions grow faster than others. Okay, so we want to show that e to the x grows faster than the given function. So it doesn't matter. Pick which one do you want to put in the top, which one do you want to put on the bottom. It makes no difference. Which, do we have a preference?
E to the x.
You want to put e to the x on the top?
Yeah.
Sure. Okay. So we want to show that it grows faster. So L'Hopital's rule. We get e to the x on the top and 3x squared. We do it again. We won't have to do this every time, by the way. I'm just demonstrating it because it's kind of predictive, right? We know if it's a polynomial, we're going to eventually get a constant, right? And then once we get that, because it's still in the form of infinity over infinity. So as soon as we get to this point, now we can see infinity, therefore, e to the x grows faster than x cubed. Yes, Owen.
So if it's like x to the n,
Yes.
and you keep doing L'Hopital's,
Yes.
it's going to be just n factorial.
So we are going to expand this to what do you think is going to happen with any exponential function versus any polynomial function? The exponential is always going to win out, right? It's always going to grow faster because any polynomial function, doesn't matter if it's x to the millionth, right? We'll eventually, if we kept doing L'Hopital's rule, it's still going to end up with a constant.
And the constant's going to be like that factorial.
Yes. Well, depending if there was already a coefficient in front, which we'll also look at factorials. Okay, we want to show that e to the x grows faster than
Do we just do L'Hopital's forever?
Do we do L'Hopital's rule forever? We don't have to. Not for this one.
Because it's gonna become negative.
Okay, well, yeah, which one do we want to put on the top?
Probably e to the x.
Really?
Yeah.
Okay.
Would you like to do
I would like to put e to the x on the bottom just for change of pace.
For demonstration purposes.
I'll put e to the x.
Well, I want to show you that it doesn't really matter. I wanted to do one of each. So if you're putting it in the numerator, you want to show that you get infinity. If you put it in the denominator, you want to show that you get 0. So I just wanted to show you one of, because sometimes if you don't know for sure, I want to show you whether you get one or the other. It's going to prove. Okay. I don't have to do L'Hopital's rule. Can I rewrite this? Yeah. Well, 3 over 2 to the x over e to the x would just be
3 over 2?
2 over e to the x.
okay. So if I can just show that that is less than 1, well, 3 over 2 over e would be what?
1.5 over 2.
Sure. 3 over 2e?
Can we just do it in a thing?
Wait, what?
3 divided by 2e.
Can we just do it in a calculator?
Yeah,
Oh.
that is true, right? I wasn't trying to overcomplicate things. So this has to go to 0, right? Because 3 over 2e is less than 1.
Because 3 is less than 2e.
Therefore, e to the x grows faster.
Why is it 0?
Pretty much.
Because 3 over 2 is less than 1.
Bro, and anything less than 1 to infinity power, you know, it's 0.
Probably gives you 0.
Kids, if I need to blow my nose, I'll be gross.
Okay, you can step outside unless you'd like it on the recording.
I think he does.
Okay.
If everyone wants to hear it, I'm happy to do it. Is there video recorded?
Yes. Okay. Now let's compare natural log of x to these two functions. So I already told you that we're going to show that it grows slower.
Ooh, slower. Let's put it on the bottom.
You want to put that one on the bottom? Sure.
So it should go to infinity.
Yeah, if we're trying to show that natural log of x grows slower and we put it in the bottom, then we should get infinity.
So it's x over 2 root x.
Okay, now this, if we look at, this is indeterminate form, infinity over infinity.
No, you should get 0. Oh, no.
No, I should definitely not get 0.
I think x over 2 root x is
1 over 2 root x
Why so long?
over,
I just wanted the screen to be recording right now.
Okay.
This is really important.
which is the same as,
x over 2 root x.
or,
Or cancel out the root x.
which is really root x over 2. Right? Because like you have x to the first power over x to the 1/2. So this gives us infinity. Therefore, natural log of x grows slower.
Will we be asked on the AP test which function grows slower? This
Yeah.
is one that we have to figure it out.
Yeah, or you might have to put them in order.
How'd you
I
get,
thought
how'd
we
you
did
get,
that on calculator.
how'd you get root x over 2?
Just powers. Because you would have an x to the first over 2 times x to the 1/2, which would just be a 1/2 power. Okay, next one. So again, we want to show that natural log of x grows slower than an x to the 6. Again, then we can conclude what do you think is going to happen with any polynomial.
Can we please
Okay.
put x to the 6 on the top of the data, please?
So which one do we want to put on the top? Again, makes no difference. You just have to come up with which one do we want to get. Do we want to get 0 or do we want to get infinity?
I like getting infinity.
You like infinity. Then that means we'll put the x to the 6 on the bottom, or on the top, excuse me. So this is going to be 6x to the 5th over 1 over x, which gives us,
X to the 4th. 6. It's been a long morning. I fell asleep.
there we go. Therefore, natural log of x grows, slower.
What if you write 6x to the 4th on the AP exam, but you still get it go slower?
Then you don't get.
Well, it depends how many points. They might have like one for the work, like finding the actual L'Hopital's correctly, and they might have one for their answer. If it's just one for the answer, they won't look at your work.
You should shove it on that. No.
Guys, not the topic right now.
Okay, next one, we want to show that x grows at the same rate.
X really grows at the same rate.
So if we want that it grows at the same rate, that means when we do the limit, we should get a real number other than 0. Okay, so there's an easier one to put in the numerator this time. Sin x.
Wait, I still get
Okay, so I'm going to rewrite this. X over x minus sine x over x. Well, this one is just going to be 1, and this is going to go to, no. Because remember, if it's sine approaching infinity, it's just oscillating between -1 and 1, so we treat this as a constant. So it's going to be 1 minus 0.
Wait, so we didn't even have to do L'Hopital's?
No L'Hopital's was necessary here. So we could just get 1.
Could you also compare the x over x?
If it's cosine x over x approaching infinity, is it still 0?
Still 0.
Okay. What about tangent? Still 0.
No, because tangent has an asymptote at every odd multiple of pi over 2. So no, we wouldn't be able to evaluate that. So x grows at the same rate as, okay. Okay, x minus 10 over x squared. I would still put that one in the numerator. So x minus 10. Again, these do not require L'Hopital's rule. If you're just putting it over x, I would just simplify it algebraically. So it would be what? 10x cubed.
Divided by x. 10x to the negative.
Thank you.
So that gives us 1.
Equals 1.
All right. Good. Right, I told you it would be pretty easy. Again, it's just a matter of getting infinity, 0, or a real number. Okay, so we want to determine whether the function grows faster than x squared as the same rate or slower. We should probably be able to make a prediction here. 12x minus 6 compared to x squared. Faster.
You guys with me.
You have to show
Yeah. So which one do you want to put on the top?
12x minus
12x minus 6? If it says determine, I mean, listen, I'll tell you on the homework, we'll come up with the shortcut. If it says to show or like verify, then you do have to do a L'Hopital's rule if necessary for these. So this will be a 12 over 2x, which gives us Therefore,
Zero, Jack.
Well, I did it the other way around.
Therefore,
x squared grows faster.
We could probably.
Can I just write grows faster?
Sure.
On the test, can I just write grows faster?
I mean, it depends what the question is asking. If it's saying determine which one grows faster, then you have to like specify. If it just asks this one's saying specifically how does x squared compare, then you could just say faster.
Wait, what is
I was cracking my neck.
I think it's gonna grow slower this time.
You think it's going to grow slower? So should we put that one on the top?
Take my hands
Sure.
off the wheel.
Wait,
You just like the slight. Nick, you ever steer with your knees?
what?
Yeah, all the
Yes.
time.
I do it pretty often.
Okay, what's the derivative of 3 to the x?
3 to the x over.
Three to the
Or
x
sorry.
natural log of three.
Oh, times the
3 to the x times natural log of 3. So we still have infinity over infinity.
I do 3 to the x.
Because that's the rule.
Project is the rule.
That is the rule for an exponential
I always
function.
forget that. I always forget that.
Okay, then we get 2, and then it's going to be what?
It's gonna be 2. It's gonna be 2 over 3x times ln 3 times L. I'll lose that.
Good? And that gives us?
The derivative of a ln of a number is just ln of a number.
No, because it's a constant. So you know.
Well, so it would be natural log of 3 times another natural log of 3. So I just put natural log of 3 squared. Look, it's just going to be a coefficient. So it doesn't really matter. The fact that we just are going to keep getting 3 to the x on the bottom tells us that that's going to grow faster. So therefore, x squared grows slower. Okay.
Do we have to show this?
This one we do not. So let's think about this. We have a 4 to the x to the 4th, a natural log of 4 to the x, and an e to the x. You want to predict. Which one's going to grow the
X to the
slowest?
No.
It's slow. It's
X
way
to the
too slow.
4.
But then, no, because these all grow at the same rate, we know that.
Wait, what?
Yeah, if we're talking
Okay.
about rate of growth. We're not talking about.
I'm on.
Okay, these are all exponential functions. 4 to the x, natural log of 4 to the x, and e to the x. So it's all going to come down to the base.
Yeah, whatever the base
Wait.
is.
Okay.
What's ln4?
So natural log of 4. What's natural log of 4
Like
approximately?
0.7.
So it's ln 4
Not-
and then e to the x, then 4 to the x.
Well, what is
Yeah.
ln?
Oh, and you were close to getting it right.
1.38629.
Oh, so that's the slowest because it's the lowest.
Okay, so that's going to go next.
You know where you were, right? I don't even have to tell you.
And then next will be
E,
e.
which is 2.71.
Yep. And then last we'll go 4 to the x. Okay. So let's expand that to slowest to fastest. So looking at the functions that we evaluated, which ones do you think grow the slowest?
Polynomials and monomials.
Okay, polynomials will be second.
Monomials.
Constants. Oh,
Natural
logs.
logarithm.
Natural
Why does
logarithms.
natural logarithms?
Okay, so logarithms grow the slowest out of anything.
After 2 derivatives.
Okay, so it's going to be first is logarithms. Actually, I lied. Not the polynomials. That's not next.
Oh, what?
Oh wait, is it the same
Oh, the
order as
radicals.
the thing we were? Is it lit?
Radicals,
It's square roots.
roots. Okay, roots are going to go in order of, and same for logarithms. It's always going to be dependent on the base. Generally speaking, in calc, we just use natural logarithms. But roots, it's going to go in order. So like, for example, a 4th root of x is going to grow slower than a cube root, which is slower than a square root.
Got it.
Good, make sense? Okay, after roots, now we have our polynomials.
Aren't roots just polynomials to a rational
Small
power? Technically.
Okay, I'm going to ignore that. Polynomials.
I was right, Loki. No, I was right.
So if we start with like polynomial at its, so what could that be? Like x squared.
And then exponential functions.
Okay.
Exponentials.
Polynomials by definition must have whole number
Really?
degrees.
By definition.
No, that.
Actually. Okay, next one is going to be our exponentials.
I knew it. I call it.
Wait, are there any more?
There's something after that.
If factorial is faster than exponential.
Finally, he got something. Okay. Exponential is going to be also according to the bases. So our slower growing would be 2 to the x, right? E to the x would be between 2 and 3, 4 to the x, and so on. And last we have factorials.
Yeah, you can be.
Okay, but how does this affect
No,
Do we
like-
have to do anything with factorials?
I don't know how to derive.
Yes. Okay, so factorials, we're going to do a lot with factorials. We don't really do much in this lesson, but just so you know, factorials grow faster. Well, what is an x factorial? So, for example, take a 10 factorial.
Why would it grow faster than like a polynomial? It was just going like x like the 10.
But that was a stupid one.
So 10 factorial.
10 times 10 is bigger than 10 times 9.
No, it's not 10 times 10. 10 times 9 times 8 times 7 times.
No, I know, but
Right.
polynomial will be 10 times 10 times 10 times 10 times 10.
But that's
Okay, so we're going slowest, right? This is going to go slowest. Oh, fastest.
52 factorial, right?